Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to be talking about gases and the fundamental gas laws. Gases are unique because their particles are in constant motion and they spread out to fill any container that they're in. They're different from solids and liquids because gases can be compressed or expanded significantly, which is why it's so important to understand how different factors affect their behavior. The gas laws that we're going to cover today are going to help us predict how gases respond to changes in pressure, temperature, volume, and the number of moles. Now, there are 4 fundamental gas laws that describe these relationships. We have Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law. Each of these laws focuses on how 2 of the gas variables interact while keeping the others constant. Once we understand these individual laws, we can combine them into a single equation called the ideal gas law. And this ideal gas law is going to allow us to solve for any missing variable when we're dealing with gases. So let's start by breaking down each of these laws one by one, starting with Boyle's law. This law describes the relationship between pressure and volume when the temperature and the number of moles are held constant. Boyle's law states that pressure and volume are inversely proportional, meaning that when one increases, the other decreases. To understand why this happens, imagine a balloon. If you squeeze this balloon, you're going to be reducing its volume. As a result, the gas particles inside are forced into a smaller space, and they're going to be colliding with the walls of the balloon more frequently. This is going to increase the pressure. On the other hand, if you let the balloon expand, the gas particles have more room to move, and that will lead to fewer collisions and lower pressure. Mathematically, Boyle's law is expressed as P1V1 is equal to P2V2. This equation tells us that the initial pressure multiplied by the initial volume is equal to the final pressure multiplied by the final volume as long as temperature and the number of moles remains constant. So if we double the volume, the pressure is going to be cut in half. If we reduce the volume, the pressure increases proportionally. Next, let's move to Charles' law. This describes the relationship between temperature and volume while keeping pressure and the number of moles constant. Unlike Boyle's law, where we saw an inverse relationship, Charles' law states that volume and temperature are directly proportional. So as temperature increases, so does volume. As temperature decreases, so does volume. So think about a balloon on a cold day. When you expose that balloon to cold temperatures, the air molecules inside the balloon are going to lose energy, they're going to slow down, and then they're going to move closer together, and that causes the balloon to shrink. On the other hand, if you heat a balloon, then the gas molecules inside are going to gain energy, move faster, and then spread out, increasing the volume. This relationship is expressed mathematically as V1 divided by T1, and that's equal to V2 divided by T2. This is telling us that the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. One important thing to remember is that temperature must always be measured in Kelvin when you're using gas law equations. This is because the Kelvin scale starts at absolute zero, so 0 Kelvin. That's the lowest possible temperature, and that is where all molecular motion theoretically stops. In fact, it was Charles' research that led to the understanding that negative 273.15 degrees Celsius corresponds to 0 Kelvin. And this is why we use the Kelvin scale in gas law calculations. Now let's move on to Avogadro's law. Avogadro's law explains the relationship between the volume of a gas and the number of moles while keeping temperature and pressure constant. This law tells us that the more gas particles we add, the larger the volume becomes. In other words, volume is directly proportional to the number of moles of gas. For example, let's say we have our balloon again, and we start adding more air into the balloon. The balloon is going to expand because we're increasing the number of gas molecules which need more space to move around. This relationship is represented mathematically as V1 divided by N1 is equal to V2 divided by N2. This is telling us that the initial volume divided by the initial number of moles is equal to the final volume divided by the final number of moles. This also tells us that if we were to double the number of gas particles or moles, then the volume will also double as long as pressure and temperature remain unchanged. Lastly, we have Gay-Lussac's law. This law describes the relationship between pressure and temperature while keeping volume and the number of moles constant. This law states that pressure is directly proportional to temperature, meaning that if you heat a gas, the pressure increases, and if you cool it down, the pressure decreases. A great real-life example is a sealed aerosol can. So if it gets too hot, the pressure inside increases and the can may even explode. This is because higher temperatures cause the gas molecules to move faster, and that leads to more frequent and forceful collisions against that container wall, and that increases the pressure. Mathematically, we see it expressed in this manner. P1 divided by T1 is equal to P2 divided by T2. So this is telling us initial pressure divided by initial temperature is equal to final pressure divided by final temperature. And again, just like with Charles' law, temperature must always be in Kelvin to ensure accurate calculations. So, thus far, we've explored the 4 fundamental gas laws: Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law. And each one describes the relationship between 2 gas variables while holding the others constant. But in reality, gases don't behave in isolation. Pressure, volume, temperature, and the number of moles are all interdependent. So how do we describe gases more completely? That's where the ideal gas law comes in. 3 of the gas laws we've covered express how volume depends on a different variable. We know from Boyle's law that volume is inversely proportional to pressure, meaning that as pressure increases, volume decreases. From Charles' law, we saw that volume is directly proportional to temperature, meaning that if temperature increases, volume expands and increases as well. And finally, from Avogadro's law, we established that volume is directly proportional to the number of moles of gas. More gas molecules mean a larger volume. By combining these relationships, we arrive at a general proportionality. That volume is proportional to number of moles multiplied by temperature divided by pressure. However, to turn this into a direct and proper equation, we need a constant of proportionality. This constant, denoted R, is called the universal gas constant. And with this, we get that volume is equal to nRT divided by P. And if we go ahead and multiply both sides by P, we get that PV is equal to nRT. And this is the ideal gas law. It allows us to calculate any of the four variables as long as we know the other three. Now, the value of R depends on the unit system that we're using. The most commonly used value in chemistry for R is 0.08206 liters times atmosphere divided by moles times Kelvin. This means that when pressure is measured in atmospheres, volume in liters, temperature in Kelvin, and the amount of gas in moles, this specific value of R ensures that the equation holds true. There are, of course, other values of R used for different unit systems, but for our class, this is the one we are most concerned with. Now that we have the ideal gas law, we can explore how to use it in different situations. So in real-world scenarios, gases often undergo changes in their conditions. Pressure, volume, temperature, or moles may shift as the gas moves from one state into another. We need a way to relate the initial and final conditions mathematically, and that leads us to an important application, the combined gas law. To derive this equation, we simply start by writing the ideal gas law for the two different states of the same gas sample. So your gas sample is going to start in some initial state. We'll call it state 1. And for that state, we can write a version of the ideal gas law where we know the initial pressure is P1, the initial volume is V1, the initial number of moles is N1, and the initial temperature is T1. Then we can do the same thing for state 2 after our gas sample has evolved. And now it has new conditions. So we write the new ideal gas law for that evolution where the pressure is now P2 and the volume is V2, the number of moles is N2, and the temperature is now T2. So we've written the ideal gas law for state 1, initial state, and state 2, the final state. Since R is a constant, for both of these equations, we can go ahead and isolate it on one side of each equation. And that gets us the following two equations. Since both of these expressions are equal to R, we can actually set them equal to each other as well. And that gets us the combined gas law, which allows us to solve for any of the variables when a gas transitions from one state to another. Now, if the number of moles remains constant, meaning no gas is added or removed, the equation actually simplifies since N1 and N2 are going to be equal. So then we have P1V1 divided by T1, that's equal to P2V2 divided by T2. And this is actually a very commonly used form of the combined gas law because it applies to sealed systems where the gas amount remains unchanged. Now, beyond predicting how gases behave under different conditions, we can also use the ideal gas law to derive equations for molar mass and density. Let's start with molar mass. Molar mass is defined as the mass of a substance per mole. And we can write this as m divided by n. Now, from the ideal gas law, PV equals nRT, we can rearrange this equation to have the number of moles on one side and all of the other variables on the other side. In this case, we get that n is equal to PV divided by RT. Then we can take this definition of moles and plug it into our equation for molar mass. When we do this, we get that molar mass is equal to mass divided by PV divided by RT. And we know that when we divide by a fraction, this is just the numerator multiplied by the reciprocal of the denominator. So really, molar mass is equal to mass times RT divided by PV. And that's the equation that you see here. This equation allows us to determine the molar mass of an unknown gas if we know its mass, pressure, volume, and temperature. Now, let's derive an equation for density using the relationship we just found for molar mass. Density is defined as mass per unit volume, so m divided by v. Now, we can take our molar mass equation that you see right here, and we're going to rearrange it. We want to rearrange it to solve for m. When we do that, m is going to be equal to the molar mass multiplied by PV divided by RT. And then we can take this and plug it into our density expression. That gets us that density is equal to molar mass multiplied by PV divided by RT, and that's all divided by V. These volume terms are going to cancel out, and we're going to get that density is equal to pressure multiplied by molar mass divided by RT. So this is our final equation for density, and it tells us that density is directly proportional to pressure and molar mass, and it's inversely proportional to temperature. So if pressure increases, density also increases. If a gas has a higher molar mass, it's going to be denser than a gas with a lower molar mass under the same conditions. If temperature increases, then density is going to decrease. So this demonstrates the three relationships that we can extract from this equation. Density is directly proportional to pressure. Density is directly proportional to molar mass, and density is inversely proportional to temperature. Now let's go ahead and jump into a couple of practice problems. This first problem says, which of the following conditions will increase the gas volume in a container? The first thing we want to do is we want to write our ideal gas law, PV equals nRT. Since we're concerned with what condition will increase the gas volume, let's go ahead and isolate this volume term. Volume is equal to nRT divided by P. From this equation, we can see that volume is directly proportional to temperature and the number of moles, and it's inversely proportional to the pressure. Keeping that in mind, let's analyze each option. A says decreasing the ideal gas constant. This is incorrect. The gas constant R is a fixed value, and it does not change under normal conditions. B says increasing the temperature. This is actually correct. Since volume and temperature are directly proportional, increasing the temperature will cause the gas to expand. B is our correct answer, but we're still going to work through C and D. C says decreasing the number of moles of gas molecules. This is going to be incorrect. Volume is directly proportional to the number of moles. So if you decrease N, you're also going to decrease volume, and that's not what we want. So C is incorrect. D says increasing the pressure. This is also incorrect. Volume and pressure are inversely related. So increasing the pressure would actually cause the volume to decrease, which is also not what we're looking for. So the answer to this problem is B. Let's move on to the second one. The second problem says a gas has a volume of 20 liters at a pressure of 1500 torr. If the volume is increased to 30 liters, what will be the new pressure? Since temperature and the number of moles remains constant based off of this problem, they don't make mention of either of those variables changing. We're really just concerned with volume and pressure. So we can use Boyle's law here. P1V1 is equal to P2V2. We're given the value for P1, that's equal to 1500 torr. We're also given V1, that's equal to 20 liters. Then we are given volume 2, the final volume, which is 30 liters, and we want to figure out this final pressure. So we want to rearrange this expression to solve for P2. P2 is going to be equal to P1V1 divided by V2. This is 1500 torr multiplied by 20 liters divided by 30 liters. Liters cancel out. We're going to get our final answer in units of torr. And if we plug this into a calculator, we're going to get 1000 torr. So the correct answer here is D. Let's move on to our third problem. Our third problem says a 5-atmosphere gas sample is initially at 6 liters and 400 Kelvin. If the volume is increased to 8 liter and the temperature is decreased to 200 Kelvin, what is the new pressure? For this problem, we want to use our combined gas law. Our combined gas law is P1V1 divided by N1T1 is equal to P2V2 divided by N2T2. Now, there's no mention of any changes in the number of moles. So that means it is safe to assume that the number of moles doesn't change, and we can go ahead and just get rid of that variable. Now we need to figure out what we're given and what we're trying to solve for. We're given the initial pressure, that's equal to 5 atmosphere. We're given the initial volume, that's equal to 6 liters. And we're given the initial temperature, 400 Kelvin. In addition, we're given the final volume, 8 liters, and the final temperature, 200 Kelvin. What we're trying to solve for is P2. So we're going to rearrange this equation to solve for P2. That means we're going to multiply both sides by T2 divided by V2. So that cancels out on this side, and now we get that P2 is equal to P1 V1 T2 divided by V2 T1. And now it's really just a matter of plugging in the values. And we know all of these values. 5 atmosphere, 6 liters, 200 Kelvin, divided by 8 liters, and 400 Kelvin. Notice liters cancel out, Kelvin cancels out. We're going to get our final answer in units of atmosphere. And when we plug this into a calculator, we're going to get 1.9 atmosphere, which means C is the correct answer. Moving on to problem 4. Problem 4 says if the pressure of an ideal gas is doubled, but the temperature remains constant, what happens to the density of the gas? we need to use the density equation derived from the ideal gas law to figure this out. And that equation says that density is equal to pressure multiplied by molar mass divided by RT. Since temperature and molar mass remain constant, we see that density is directly proportional to the pressure. So if the pressure is doubled, the density also doubles, which makes the correct answer for this problem C. And now we can move into our last and final problem for this section. This problem says a 44-gram sample of a gas has a pressure of 2 atmosphere, a volume of 11 liters, and a temperature of 100 Kelvin. What is its molecular weight? This should say molar mass. So we're going to be using our molar mass equation to solve this problem. That equation says that molar mass is equal to mass multiplied by the ideal gas constant multiplied by temperature, and that's divided by pressure multiplied by volume. In the problem, we're given the mass that's equal to 44 grams. R is our ideal gas constant, which is equal to 0.08206 liters times atmosphere divided by moles times Kelvin. We're also given temperature, that's equal to 100 Kelvin. Pressure is equal to 2 atmosphere, and volume is equal to 11 liters. So we're given all of the values we need to just plug these into the equation and calculate. Something to notice here is that our liter units are going to cancel out, our Kelvin units are going to cancel out, and our atmosphere units are going to cancel out. What we're going to be left with is grams divided by moles, which is exactly the unit we want if we're calculating molar mass. If we plug this into a calculator, we're going to get 16.4 grams per mole. So answer choice B. Now that we've explored the ideal gas law and its applications, let's take a closer look at what happens when we have a mixture of gases. Many real-world systems contain multiple gases that do not react with each other, like the air that we breathe. It's a mixture of nitrogen gas, oxygen gas, and other trace gases. When gases are mixed in a container, then, how do we determine the contribution of each gas to the total pressure? This is where Dalton's law of partial pressures comes in. Dalton's law states that in a mixture of gases, the total pressure is simply the sum of the pressures of each individual gas, assuming each gas behaves ideally. This means that each gas in a mixture behaves as if it were alone in the container and it was contributing to the overall pressure independently. We can write this mathematically. The total pressure, PT, is equal to PA plus PB, so on and so forth, where these indicate the partial pressures of the individual gases in the mixture. Now, how do we determine the partial pressure of a specific gas? To do that, we need to use the concept of mole fraction. The mole fraction of a gas, let's say gas A, this is going to be equal to the ratio of the moles of that gas to the total moles of gas in the mixture. Then once you know the mole fraction of gas A, you can now calculate the partial pressure of that gas using this equation. The partial pressure of gas A is equal to the mole fraction of gas A multiplied by the total pressure of the gas mixture. Now, this is best understood by tackling an example problem. This one says a gas mixture is found to be 4 parts nitrogen, 1 part carbon dioxide, and 1 part oxygen. If the total system pressure is 2 atmosphere, what is the partial pressure of nitrogen? Let's start with writing down what we know and what we need to figure out. We are given a gas mixture containing 4 parts nitrogen, 1 part carbon dioxide, and 1 part oxygen gas. In addition, we're told that the total system pressure, PT, that's equal to 2 atmospheres. Our ultimate goal? To figure out the partial pressure of nitrogen gas. The partial pressure of nitrogen gas, that's going to be equal to the mole fraction of nitrogen gas multiplied by the total pressure. We know the total pressure. What we need to figure out is the mole fraction of nitrogen gas. The mole fraction of nitrogen gas is going to be the moles of nitrogen gas divided by the total number of moles. We can treat these parts as mole information, so we can sum them up. 4 plus 1 plus 1, that gets us 6. That's going to be our N total. And then our number of moles for nitrogen gas, that's going to be 4, since we have 4 parts nitrogen gas. So we plug that in. 4 divided by 6, this is equal to 2 divided by 3, which is approximately 0.666, so on and so forth. We're going to take that value, we're going to plug it into our partial pressure of nitrogen gas. That's going to be equal to the mole fraction, which is 2 divided by 3, or 0.6666, multiplied by the total pressure of the system, which is 2 atmosphere. And then when we plug that into a calculator, we're going to get 1.33 atmosphere. So that is the partial pressure of nitrogen gas in this mixture. Now that we've explored gas laws and partial pressures, we want to shift our focus to another concept in chemistry, and that's going to be balancing chemical equations. A little bit of a different turn here, but bear with me. Chemical reactions, they have to follow the law of conservation of mass, and that states that matter cannot be created or destroyed in a chemical reaction. This means that the number of atoms of each element in the reactants has to equal to the number of atoms of those same elements in the products. Therefore, balancing equations ensures that the reaction accurately represents how atoms are rearranged without losing or gaining any. We're going to learn today how to apply this to a combustion reaction, which involves substances burning in oxygen gas to release energy. And we're specifically interested in the combustion reaction of hydrocarbons. When a hydrocarbon, a compound made out of carbon and hydrogen, undergoes complete combustion, it reacts with oxygen to produce carbon dioxide and water. To balance an equation systematically, including combustion reactions, we follow these 5 steps. The first step is to determine the reaction that's occurring. You want to identify the reactants and products, and you want to include their physical states. Are they a solid, liquid, gas, or aqueous? This helps in understanding what species are involved in the reaction. In step 2, you want to go ahead and write the unbalanced equation that summarizes the reaction described in step 1. So you want to list all of the reactants and the products without worrying about coefficients yet. Now, these first 2 steps you have to do if you're not given a chemical equation. In my class, if you're a student taking my class right now, we will be given the chemical equation. But for thoroughness, I wanted to go over these steps nevertheless. Now, step 3 tells us, okay, you have your unbalanced chemical equation. Now it's time to balance one atom at a time. You want to start with the element that appears in the most complex molecule. So typically the one with the most elements in it. And from there, you want to start to balance that atom. If necessary in this step, you can use a fractional coefficient to balance the simplest substance. Now, after you've balanced one atom at a time, now we can move into step 4. Step 4 tells you, well, ultimately, to have a correct, balanced chemical equation, you can only have whole number coefficients. So if you had used any fractional coefficients in step 3 to help you balance the chemical equation, it's now time to get rid of that. To get rid of those fractional coefficients, you want to multiply all of the coefficients by a factor, the same factor that eliminates fractions while keeping the equation balanced. Finally, you want to double check that all of the atoms are balanced. So count the number of atoms of each element in the reactants and products to confirm that they are equal. Now, again, this is another topic that's best learned through an example problem. And here in our last page, we have one more practice problem regarding partial pressures, and then a final problem that relates to balancing combustion reactions. So let's go ahead and get started. The first one says a gas mixture consists of 4 moles of hydrogen and 6 moles of helium. If the total pressure of the mixture is 40 atmospheres, what is the partial pressure of hydrogen? Of course, we want to start by writing down what we know and what we want to figure out. We're told we have 4 moles of hydrogen gas and 6 moles of helium. In addition, the total pressure of the mixture is 40 atmosphere. Our goal is to calculate the partial pressure of hydrogen. That's going to be equal to the mole fraction of hydrogen multiplied by the total pressure of the system. We know the total pressure of the system. What we do not know is the mole fraction. So we want to start by calculating that out. The mole fraction of hydrogen is going to be the number of moles of hydrogen, which is 4, divided by the total number of moles in the system, which is 4 plus 6, and that's equal to 10. So we're going to leave our mole fraction in this form, 4 divided by 10. We're going to plug that in here, and we will be multiplying this by the total pressure of the system, which is 40 atmosphere. This is a really easy calculation to do on your own. We can simplify these two values here, divide this by 10 to get 1, divide this by 10 to get 4, and then we're left with 4 times 4, which is equal to 16 atmospheres. So the partial pressure of hydrogen is 16 atmospheres, so the correct answer here is A. Moving on to our last and final problem for this lecture. This problem says, what is the correct coefficients for the combustion of propane? Propane is C3H8. So to determine the correct coefficients for the balanced combustion reaction of propane, we need to recall that combustion reactions always involve oxygen gas, and they produce carbon dioxide and water. Now, to balance this reaction, we're going to start with balancing the carbon atoms on the reactant side and on the product side. On the reactant side, propane has 3 carbons. On the product side, we only see carbon present in carbon dioxide, and there's only 1 carbon. To balance the carbon atoms, we're going to place a coefficient of 3 in front of carbon dioxide. So now we have 3 carbons on the reactant side and 3 carbons on the product side. Next, we're going to balance the hydrogen atoms. On the reactant side, we have 8 hydrogens. On the product side, we only have 2 hydrogens. To balance this, we're going to add a coefficient of 4 in front of water, and that allows us to have 8 hydrogens on the product side that matches the 8 hydrogens on the reactant side. So we've also noticed we've kept just a coefficient of 1 in front of propane. We didn't need to add any coefficients in front of this. We just did that for carbon dioxide and water so far. All we have left now is oxygen. So on the reactant side, right now we have 2 oxygen atoms. And on the product side, we have 4 oxygen atoms plus 6. So we have a total of 10 oxygen atoms on the product side. To make sure they balance each other out, we're going to add a coefficient of 5 in front of oxygen gas. Now we have 10 oxygen atoms on both the reactant and product side. And now everything's balanced. This is a balanced chemical equation, and the coefficients are 1, 5, 3, 4. So answer choice C. And with that, we've completed this lecture. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.